Uh, well, hello everyone. Thank you again for coming along to one of our, hopefully two of our Theoretical Sciences Visiting Program thematic session talks this afternoon. I noticed it's a bit sunnier out there, so we've drawn the curtains, which is quite exciting. Obviously means the weather's going in a positive direction. So anyway, it's my absolute pleasure to introduce Professor Karen Abbott this afternoon. Karen is a professor and associate chair at the Department of Biology at Case Western Reserve University in the United States. And Karen does all kinds of really cool work, particularly about tipping points and that kind of stuff. So I believe that's what she's going to tell us about today. So I'm really excited. So yes, please, Karen, take it away.
Thanks, Sam. And yeah, thanks everybody for coming. I'm sorry that I've drawn you into a dark room, but hopefully I will say some interesting things in the next little bit. So we are going to talk about tipping points today. And the context here, I think the ecologists in the room will be very familiar, but realizing that this might be a little bit of an interdisciplinary audience, I want everybody to be clear on what I'm talking about. So the statement at the top, ecological systems can show dramatic changes in state or behavior. We see this kind of thing, we call it a regime shift. And it's some familiar examples are here where coral reefs can shift suddenly from a coral dominated state, which has a lot of fish, to an algal dominated state where the growth of the algae has outpaced the fish's ability to clean it off the rocks. We also see a woodland grassland transition of a similar sort of type in savanna ecosystems. And in freshwater lakes, this is an experimental lake. So this is a barrier between a manipulated and a non-manipulated lake where we see alternative stable states of clear water or oligotrophic or, again, algal dominated. So this is the kinds of things we're talking about when we say regime shift. It can mean very different population sizes, different combinations of species being present. So a shift in the community structure, different species dominating, et cetera. And these regime shifts occur when the system crosses a threshold of some sort that's called a tipping point. But the threshold can be a threshold, as I have here, a threshold in what? Sort of depends on what type of tipping point. And so to walk us through some of the different types of thresholds, some of the different types of tipping points, I'm going to turn over the next couple of slides to everybody's favorite super genius, Wile E. Coyote. So for anyone here who wasn't raised on American cartoons, Wile E. Coyote is a cartoon coyote who has a preferred prey item with an extremely long handling time. In this Roadrunner, and see, but this is a very serious science talk, so I have Latin names up there also. So the coyote chases the Roadrunner all over this beautiful Western United States landscape full of cliffs and valleys. And if the coyote taught us anything, he taught us that there's more than one way to fall off a cliff. And the analogy here is that there's more than one type of tipping point. And the analogy is actually surprisingly good. So we're going to use the coyote to talk about two different kinds of tipping points first, that will probably be familiar to many people, and then a third that might be unfamiliar. Okay, so to make this rigorous, we are going to imagine that the cliff has some properties that are governed by the parameters of a system. So this is like environmental variables or what have you in the real ecological world. Here we're talking about the properties of the cliff, and then we have some state. Of course, if we're looking at a regime shift, we're interested in the state of the system. So what is our state variable in this cartoon analogy? It's the position of the coyote relative to the edge of the cliff. And the state of being on the cliff has some basin of attraction, in that if the coyote is there, so it begins wherever we say the cliff began and it ends at the cliff edge. And if the coyote is somewhere in that basin of attraction, it is stably attracted to the state of being on top of the cliff. If it crosses out of that basin of attraction, there is an alternative stable state that it will fall to. Okay, so the first way to fall off a cliff is that there is something called B-tipping, and that's the top of these two scientific diagrams. So in B-tipping, the idea is that the parameters of the system change in such a way as to cause the stability properties to change. Here, our stable state has, it's not even an unstable equilibrium. It's not even an equilibrium anymore. There is no basin of attraction associated with being on top of the cliff if the whole cliff breaks off. And then the coyote's still on it, but it's not in a basin of attraction for remaining on the cliff top anymore. The B in B-tipping comes, I believe I just said this word as well, comes from the word bifurcation from dynamical systems, which refers to this type of qualitative change in stability properties. So B-tipping occurs when the cliff, the environment, experiences a bifurcation such that what had been a stable state, stable equilibrium state, no longer is one. And this is the classic ecological tipping point. So the lake eutrophication example that I showed you that's so famous, and the coral, et cetera, those tend to be usually, if you see tipping point in ecology, even if it's not specified, usually we're talking about B-tipping. Another type of tipping is N-tipping, where the N here refers to noise. And this is the idea that there is some exogenous perturbation to the state of the system. Here, I realize this is a little misleading. Here, I found a picture of the roadrunner making an actual noise, but I mean stochasticity, not meep, right? But anyway, it perturbs the state of the coyote so that it is now no longer in the basin of attraction. So unlike B-tipping, where that basin of attraction just disappeared, it's still there, but the coyote's not in it, right? So again, very conceptually straightforward. We all got this as children watching cartoons. So now the state of the system, the coyote's horizontal state, has moved, so it's outside of the basin of attraction. And this type of tipping, N-tipping, where the stable state we had been in is still there, we're just not in it anymore, is always a risk when we have alternative stable states, because there's always some possibility that stochasticity will push the system from one basin of attraction to another. So these two are, as I said, probably familiar. Another type of tipping point that is perhaps unfamiliar is this idea of R-tipping. And for R-tipping, I had to stretch this analogy a little bit, because if there's an episode on this, I didn't see it. But here, what is happening is the properties of the cliff aren't changing, or maybe they're changing, but not in such a way as to cause a bifurcation. It's not snapping off or changing stability properties. And the coyote's position's not changing, but the location of the cliff itself is changing through time. And so to avoid tipping, to avoid going off the edge of the cliff because the coyote stayed still, but the cliff moved, the coyote's got to run. And the thing that determines whether there's a tipping point here is the relationship between the rate at which the cliff is moving and the rate at which the coyote can run. If it can't run fast enough, it will fall off the cliff. And that is called R-tipping, in this case, the R standing for rate, so rate-dependent tipping. And to say that in non-cartoon words, what we're saying is there's still a basin of attraction for an ecological state out there, but the system's own dynamics were not fast enough for it to track this moving equilibrium. So different from B-tipping, because in B-tipping, we lose the stable equilibrium. In R-tipping, it's still there, but we might not be able to keep up with it. So, okay, coming back to, thank you, Wile E. Coyote, coming back to me as the person telling you things. This is the statement I began my talk with. Regime shifts occur when a system crosses a tipping point. And the outline for my talk essentially dissects this statement. It's a very obvious sentence on its face, but I think there's a lot of interesting stuff embedded in it. So we're going to start by targeting this question of what determines the regime we're in the first place. So if we're thinking about tipping, the flip side of that question is, why are we staying somewhere to begin with? Sort of what's creating the regime, and therefore what must have sort of failed to keep us there when a tipping point does occur, right? So we're going to start by thinking what determines the current regime. Of course, it's the interplay of deterministic feedbacks and noise. That's the answer to probably literally every question in ecology, but there's not a lot of content in that. But it is an interplay between deterministic feedbacks and noise that stabilizes a particular state, and that could be an equilibrium, but it could also be a persistent transient. So I'm actually going to start by taking this word stabilizes, which is in quotation marks, because I'm including things that might not literally be stable equilibria in this category, and ask, what do we really mean by stability, or what should we mean by it, and how should we measure it? This is something that some of my fellow thematic program members have talked about a little bit, and I will probably be the most obsessed with trying to lead you through sort of an examination of what we mean by stability. So once we finish the first word of this sentence, we'll hop to the end, and I'll finish up my talk by looking at tipping points explicitly again by asking, can we take our understanding of what maintains regimes, turn it around, and use that to understand essentially what makes us lose regimes or what makes us tip? And this is where I think we can do a bit of conceptual unification of transient dynamics, what's keeping us in a regime for some meaningful amount of time, and tipping points. So this is where we're headed. We're going to start here. What does stability mean in natural systems? I am far from the first person to ask this question. I'm not even the first, as I said, in this group. But one of my favorite attempts at answering it is this paper that's now fairly old, that cataloged at that time, and I'm sure it has only gotten worse, the number of different ways ecologists used the concept of stability. And they found 163 unique definitions of stability that they then tried to categorize, that's maybe counting literally everything as different if you kind of put it in slightly different terms. So they really tried their best to bring that down to a reasonable number, and they ended up with 70 different concepts of stability. This is their list. We're not going to go through it, but it's even when they tried to, put order on this by putting things in categories and collapsing things, they still had things like 17 definitions of resilience. And as I said, I'm sure it's only gotten worse. So I'm going to do more. Just kidding. We're not going to go through this big long list, but this bugs me and I love it, right? So stability means a lot of things, and I think it should, because we're trying to come up with maybe a single number or a small suite of numbers that summarize an extremely complex attribute of an ecological systems. So I think it's okay that when we think of stability, we think of lots of different things. I mean, it maybe is not great for our ability to communicate those things. I don't think we need a single best measure of stability, but I do think we need better ideas of understanding how these different concepts relate to each other. And that's where I'm going to spend a few slides. So I think a really useful way to pull together a lot of these different stability concepts and understand their relationship is to use the potential landscape. Again, I'm far from the first person to suggest this. The potential, I've drawn a potential for a one-dimensional system. So we're tracking the dynamics of a single species here. And if you are a mathier person who's used to seeing dynamics written in terms of change in population through time, dNdt, that's the formal mathematical definition of this function u that I've plotted. If you're not a mathy person, just look at the graph. And it's the thing I like about these landscapes is they're extremely intuitive. And so for this one that I've drawn, we can imagine how the dynamics will play out in this system that's described by this particular function u by imagining that we have a ball somewhere on this surface and we let it roll. And so I'm going to just show you, because people are most familiar often looking at dynamics in terms of time series, what happens if I start this population at a size of 10 and just let it roll. Well, it's just rolls to the bottom of the well, what I've marked as 50, and our time series with that initial condition in the stability landscape would look something like this. So this is what we're depicting for anybody who hasn't seen or isn't super used to thinking about a stability landscape. On this landscape, we can pick out some key features. So any local minima are stable equilibria, and any local maxima are unstable equilibria, places where the ball would stay if you balanced it right at that spot, because it is flat there, but where it will roll away rather than towards if we perturb it a little bit. So using this kind of landscape, we can talk about different ways to measure stability, and we're not going to do 163. We're just going to do a small handful. But one thing we sometimes mean as ecologists when we say stability is the ability of a system to persist, so to avoid extinction. And if we had this kind of landscape and we wanted to measure the ability of a system to avoid extinction, We might look at the slope of the curve near zero. I have helpfully not labeled, but imagining that this is a population size of 0. And the steeper the slope there, the faster a system that's close to extinction will roll away and recover. So in this situation, we would imagine we would consider a system that looks more like that to be more stable by this measure of stability than the other one. We could also look at the size of the basin of attraction in a couple of different ways to measure stability of that local minimum. So we could look at basin width, where a wider basin is more stable than a narrower one, because there's a wider range of system states that would still ultimately recover back to that equilibrium. We could also look at basin depth, and this says sort of how much you have to push the ball uphill. What's pushing the ball uphill? Well, perturbations, random things that aren't the internal dynamics of the system. So how big of a perturbation essentially do you need to get out of this well? A deeper well would be more stable than a shallower one. This is Holling's resilience that he described in a paper, but except for 1D wasn't able to measure it. I'll get to why in a second. The rate of return to equilibrium is an extremely common measure of stability. So for those of you who have done some theoretical ecology, which I know is many people in this room, but probably not 100%, if you've calculated the eigenvalue of the Jacobian matrix linearized at this equilibrium, this curvature is what you are calculating. And by that measure, something that's more concave is more stable. It will, if you're relatively close to the bottom of that well, so this is a local measure, but if you're relatively close to the bottom of that well, you'll roll back to equilibrium faster than if it's flatter by this interpretation. And then, you know, we could go on. My slide's about to be full, so I'll stop. But we often think of things that have a single stable state as more stable than things with lots of stable states, because if you have one global attractor, then you'll end up there, you know, hypothetically, if you wait long enough. So I mentioned that this is really the most commonly used measure of stability. It's that sort of because we've borrowed a lot of our ways to understand ecological dynamics from dynamical systems math, and this is a very straightforward and nicely interpretable quantity. They're great. Don't stop calculating eigenvalues, but I think it's important for us to realize how limited they are. So if we have this whole landscape, and this is the measure of stability we use for that one stable equilibrium I'm showing, what we're doing is we're looking at the range of population sizes that is close enough to the equilibrium that this straight line is like reasonably close to the curve. So you use your judgment. Does it have to be where I've drawn the lines really overlapping? Is out here okay? I don't know, whatever. There's not a hard cutoff. But the point is that we're looking at where this is flat, and it's only flat exactly at the equilibrium. So we're looking in that neighborhood, right? And so that's like saying if we had this whole stability landscape, I only care about this little slice, and I'm going to ignore everything else, right? That's silly when I put it this way. So not that this is silly, but it's limited. And there's lots of different ways to think about stability. And if we have this whole landscape, we can get a lot more out of it than just saying, like, how curved is the little bottom of my well. So with that hugely influential, I'm sure, sales pitch, why don't we use potentials all the time in ecology? You see the diagrams drawn all the time, but as mathematical objects, we don't use them very much. And the answer why is that for systems of more than one species, we usually don't have a potential. And I can explain to you why conceptually. We don't have to do the math to see why. So now I'm drawing, I'm just calling it a landscape because it may or may not be a true potential, depending on what I tell you about it. That's now a surface in 3D. So we have two state variables instead of just a single population. Here, predator and prey. If we had a system where a ball started somewhere away from this minimum, just rolled straight downhill. So our time series would look something like that. I mean, this is just hand-drawn, but you get the idea. Straight downhill. If that were the case for this system, the surface I've drawn would be a true potential, okay? However, getting to why we often don't have a true potential, if instead the ball is gonna swirl down the bowl to the bottom, which is almost always what we have in consumer, even if there's a stable equilibrium and these are going to flatten out, there's usually these damping oscillations. Ecological dynamics are nonlinear, and that's what happens. If we have this kind of swirl, then what I've drawn is not a true potential. And the reason I'm claiming that, and the way to understand it, is that if I just showed you these two bowls without a little line that I drew that says the trajectory, you wouldn't know if there's a swirl or not, which means that in the case where there is a swirl, that bowl is not giving you full information about the dynamics. You're missing that piece of information about the fact that there's a swirl. So therefore, it's not encapsulating everything about the dynamics, and definitionally at potential it needs to. So we don't usually have a potential function for ecological systems with more than one state variable, which makes this limited to single populations and very special cases of higher dimensional systems. And so people just draw these landscapes and say, imagine a ball, and it's just an analogy, right? But it's such a powerful mathematical framework that one of the things we've done in my lab is to develop the use of the quasi-potential as a sort of stand-in for this potential. So what a quasi-potential is, it's unfortunately something you have to compute numerically. It's not a function we can write down in most cases. If there is a potential for a system, then it recovers. This method of computation just recovers the potential. But if there is not a true potential, what it does is it uncovers the downhill bit. So it recovers that bowl and throws away the information about the swirl, right? And I'm showing you an example of quasi-potential there, really just because it's a pretty picture that my former postdoc made. But what we imagine is we can compute these surfaces from the deterministic skeleton of a noisy ecological system, and then imagine that there's a ball rolling on it and it's sort of being jiggled by noise. So we get the downhill dynamics. This is another example where there's a vector field mapped onto the heights here that show us that a ball rolling here inside this deep well, or at least to the side of the local maximum of that deep well, will make some path to this local minimum. This vector field with the quasi-potential doesn't tell us, or the surface doesn't tell us how it's going to get there. So we can also recover the remainder vector field, which is composed of information about circulation at level heights on this surface. And if you put those together, you get the full dynamics back. What we tend to do is do this decomposition and then throw this out. Not because we don't care about cycles, but because ultimately we're interested in using this method to measure stability of an attractor, where we want to know sort of about the geometry of this basin, and we're less concerned about the path the system will be taking within that basin. Just as a quick tease, because I just think this is really cool, you can also compute quasi-potentials for systems. This is the quasi-potential for the Loch of Volterra, might be Rosenzweig-MacArthur. It's some sort of predator-prey model that has a stable limit cycle. So there's a track at the bottom. It's all the same height. There's not a unique local minimum. It's an orbit. In the real dynamics of the system, the ball is going around this track, but it's moving around by a force that's not represented in the surface because it's just a level. But anyway, you can get potential-like things for non-point attractors, and I think that's wildly cool. So ways to measure stability. If we have a quasi-potential, we can do the things we were mapping onto the regular potential that I started as part of my talk with. So here's the quasi-potential for a predator-prey model. I always show the equations for those who are interested. I'm not going to belabor them, though, because I'm interested really in having you guys follow the conceptual side of what I'm saying. This is the quasi-potential for the deterministic part of the dynamics, and we're adding some noise on there. This particular model for the parameter set that I'm showing has two stable states. I'm labeling them A and B. And if we were to compute a dominant eigenvalue of a Jacobian evaluated to each of these stable states, we would get the classic measure of stability by which we would consider, here I'm showing the negative return rate so that a higher bar is more stable. By this measure, the sort of classic measure of stability, B is quite a bit more stable than A. But if we instead do Holling's resilience measure of stability, where we're looking at the height of the basin relative to the local maximum that separates them, then we actually see that A is much more stable than B. So we get different answers depending on which measure of stability we're interested in. This begs the question of which should we care about. And for the kinds of questions I care about, here's how we answered that. So I'm going to show you a simulated time series of this system. It goes for quite a long time. And before I show you the trajectories, let me orient you to what I'll show. So we have 2 species and 2 equilibria. So I'm going to mark 4 lines on this plot. Equilibrium A, when we're there, this is the equilibrium level of species 1, and this is the equilibrium level of species 2, and then the same 2 lines showing species 1 and 2 at equilibrium B. And if I pop up a time series here, of course, this is just one realization, but we did this in a more rigorous way. It's also like smack you over the face obvious that the populations are spending way more time at A than B. There's enough noise that they are moving back and forth. But when they move to B, they tend not to stay very long. And when they get to A, they stay for longer. And so if we're interested in stability from the standpoint of if we're in this state, are we likely to stay? Or from the standpoint of if I go out and observe this population at some arbitrary time, what am I likely to see? By those types of In those types of questions, A would be the much more valuable measure of stability than B. A would be much more stable than B, so the second one would be much more useful measure of stability than the first one, but we always do the first one, so what I'm saying is we should calculate quasi-potentials and do the second one more, or at least think about stability in a slightly different way. So where we've gotten so far is to talk about one word that's part of some more words that go back to one word, but don't worry, it won't take us so long to get through the rest. Stability here means a lot of things. Stability in ecology means a lot of things. That's okay. But the thing that I sort of like to proselytize is that global measures of stability, and by that I mean global and state space, so not just looking super, super close to the equilibrium, but thinking about all the possible population sizes you may see, or values of whatever state variable you're interested that you may see. These global measures of stability are likely to be more relevant than local ones, given that we live in a noisy world. Okay, so we're ready to entertain this next one, and each of these bits gets shorter as I go, so don't worry. Okay, what puts us in a particular regime? In other words, why do some states last for a long time, or what makes a system stay where we are? Well, we can use quasi-potentials. I'm just going to show you a lot of hand-drawn potentials because, again, I'm going after conceptual understanding here, and these are easier to look at than anything in 3D. The places where we're likely to stay are, if you guys were a class of undergraduates, I would have made you tell me the stable equilibria, right? Obviously, the places the ball is going to tend to roll to, we're probably going to spend a lot of time there. That is true. And those stable equilibria are created by density dependence that's going to counteract any perturbations that try to move the ball away. But that's not all. A neglected, but I think equally important part of the story, more neglected, but equally important part of the story, is the idea that anywhere where we're responding to a perturbation relatively slowly means that we're going to move away from where we are relatively slowly. And the other places on this where we're likely to spend a lot of time are where the curve is flat or close to flat. And so the curve is exactly flat at an unstable equilibrium. When an unstable equilibrium looks like that one I've drawn that has sort of a flat-ish plateau around it, we don't expect a system that has happened to get to that unstable state to move away all that fast. So we're likely to see a long transient near an unstable equilibrium that looks like that. We're also likely to see long transients around states like this where there's no equilibrium. There's no place in that stretch I've shaded that is perfectly flat, but it's pretty close to flat. We have these, like, again, sort of plateaus in the potential. So that's a way to understand it through analogy, and we'll talk about what types of ecological properties create these spots. But the thing I want you to kind of take away from here is that we're likely to a regime, a dynamical, a dynamic that we're likely to stay in, or a state we're likely to stay in, is one where this sort of representation of the dynamics gives you a flat or flat-ish spot. So flatness, the answer to why we have a regime is flatness. So there's 2 different ways to be close to flat that are pretty simple, and I'm going to just quickly walk you through each. Okay, so this is the statement we've just said. The stability landscape is flat at equilibrium, so it's almost flat if we're almost at equilibrium. If we're looking for places that are close to flat, we should look close to equilibria. There's two different ways to be close to equilibrium. One is there is an equilibrium and we are close to it. And that is that can happen for any type of equilibrium, but we're particularly interested in considering saddle points. And a saddle point, which is so named because around there is a perfectly flat spot here, so an unstable equilibrium right in the middle of that shape. The quasi-potential or potential around it has a shape more or less like a horse's saddle, where there's an axis where it's at the bottom of a U, and then another axis where it's at the top of the U. And so saddle points are interesting because we could hang out near any unstable state, because any surface feature near any unstable equilibrium would be pretty flat, at least locally. But then we have the question of, well, biologically, why would we ever end up in that state? Saddle points give us a reason to say this is relevant. I think we could end up in that state because there are a set of states by which the system will first move toward the equilibrium before moving away. Oh, I thought I had a cute animation. Never mind. In this case, the ball that I start there will roll toward the saddle point first before ultimately rolling away. And the little crawling guy there is to represent what we call a saddle crawl by. People in the literature had previously been calling these saddle flybys. That sounds fast, so we changed it to remind us that it's slow, because it will roll quickly when it's on the steep part there where I have multiple arrows. Slowly, when it gets to the flat part, it will still be rolling away, towards and then away. It'll still be rolling past, but potentially quite slowly near the saddle. And that could create that saddle point as a long-lived transient. And there's a few papers where we've explored that phenomenon in more depth if you're interested. But okay, this is one way you can be flat. You can be close to equilibrium in that there is an equilibrium here, the saddle point, and you are close to it. The other way to be close to equilibrium is to say there is no equilibrium where you're at, but if the conditions were just a little bit different, there would be. So close to equilibrium in a different way. We call this a ghost, and others have also called this a ghost. And this is the idea that in this quasi-potential I've drawn, there's an almost flat spot here. It's still downhill. You will roll if I start a ball here into the one stable state. But if I change the parameters just a little bit, change the environmental conditions just a little bit, we'd have another little local minimum here. So we don't have an attractor here, but we almost do. And in the interest of time, I will not walk you through the details of this, but here, what am I looking at? Competitor one, it's a competitive system. Competitor one is stably in the system. There is a basin of attraction related to that. And here, the only stable equilibrium is for species one to be extinct, but we have a long transient phase where it persists due to a ghost, because these conditions are similar. Okay, I got about 4 minutes left, which should be just about right if you guys aren't getting too tired. If you are, it's only 4 minutes left. So what did we just learn? We learned that regimes are, yes, stable states. I'm not dismissing that possibility. I'm just not talking about it a lot because it's pretty obvious and well studied. So in addition to stable states, regimes that we see out there are also other states associated with slow change, that is long transience. And so what we need to bear in mind is that the history is going to determine sort of where on that landscape we are, where's the ball in the first place. And then that landscape itself, the thing that's governing, are you moving quickly or slowly towards ultimately a stable state, is going to determine whether you're sort of hanging out in something that might be considered a regime, a long-lived state in our observations, or not. Okay, so hopping to the end here and thinking now, can we take what we understand about what maintains the regimes and use that to understand tipping phenomena? I started this talk with an explanation of 3 different types of tipping points. And now that you guys are experts on reading potentials and quasi-potentials, I'm going to do a quick recap So we saw this example already. What we were looking at was a case of end-tipping. We never lost equilibrium A or B. There was no change to where those lines were. It's why they're just flat lines in this graph, but noise was moving us between the two. And that would look more or less like this. It's not literally the same simulation, but the black squiggle on here is a trajectory that starts in B, hangs out for a while, and then goes to A, similar to that piece of the time series I've highlighted. B tipping is a situation where we actually do lose an equilibrium state, or it changes from an unstable to an unstable state. So this is a quasi-potential for Lockwood-Volterra competition for anybody that's interested in knowing that. You can just think of it as an arbitrary two-species system. And if we have a change in the external conditions, say the strength of competition between these two species, we can convert from a quasi-potential with one well, a stable coexistence that looks like that, to this would be priority effects. Now we have two local minima, and it's the two cases of one species excluding the other. And so if we had this type of bifurcation in a system that had been at that equilibrium, we can sort of translate the ball down to the same spot on this new surface and see where it rolls. In this case, because of where we started it, the ball is going to roll this way if there's no other perturbations, just that bifurcation. And we've seen B tipping from coexistence to species one being excluded. R tipping is probably conceptually the most difficult. Some of you maybe have only heard about it for about 35 minutes. So again, we can think about starting with, so I'll do a competitive system, but here let's say species one is sort of stably excluding species two. There's enough species two around, it could grow back, maybe just being randomly introduced at some low level. And for R tipping, we're imagining that this surface is changing, but not qualitatively. This is like I inverted the whole thing. That's a big qualitative change, the middle column. Here we're always going to have those two wells. Just the location of them in this state space is going to move. So let's say we just shift the whole thing really fast, like so fast that this ball that I moved down hasn't done any rolling yet. And now we find ourselves in this situation. In this case, we're going to R tip because we had species one being the winner, and now we're going to have species two being the winner. If I make that same magnitude of change more slowly, or due to the limitations of my animation skills in short chunks, so we move it a little, we let the system recover, and we move it some more, and we let the system recover. This is the same total amount of change, but now we have not R tipped. Okay. Basically out of time. Do you guys have 3 more slides in you to hear more about R tipping? I see 2 thumbs up and nobody running for the door. Okay, this is actually my favorite part of the talk. I put it at the end because I don't think it makes any sense unless you guys listen to everything that I just said. But here's where we are, and this is where I'm sort of actively thinking about things. So slow dynamics is what causes long transients. Duh, we know that, flat spots. Slow dynamics is also what creates the risk of rate-induced tipping. It doesn't have to be slow, but too slow to keep up, right? And so what I wanted to do is take a really nice model from the applied math literature and try to kind of force it to be an ecological model. It's not a very good ecological model. If anybody knows about this stuff and wants to sit with me at some point and help me make this into a better ecological model, I'm really keen on that. But for now, just sort of hold your nose and listen to me talk about this model for a couple of slides. So this is a sort of a model of invasive species in that the equation's up there. It says that we have like some low density, I'm calling it kind of a, in quotes, carrying capacity, where K, where if the invasive species was at that level, like that would be okay with us. We're usually not looking for complete eradication for invasives, that's too much. And then we have some constant rate of harvesting H in there as well. And there's a stable equilibrium here that line depicts. And if we start above or below it, we'll converge on the stable equilibrium. However, there's also, and so let's say, because K is good enough, and this is a little below K, we'll say control, invasive control succeeds. There's also an unstable equilibrium here. And if we are on the wrong side of it, this population actually grows, this model will grow to infinity. So we're not going to worry about the infinity. Obviously, something would stop it at some point, but we're just going to say control fails if we find ourselves on that side of this boundary. The potential for this function looks like this. That's the hump we don't want to cross over, because then it just rolls downhill to infinity on this population axis, and that's the stable state. where we say good enough control has succeeded. So we have two knobs to turn here because there's two parameters. We could increase the harvest rate, or we could try to make the habitat less hospitable so that we decrease K. And the way that the solid line here and 1 star, the stable one, and the dotted unstable one will change, with K in that way. If we decide to decrease K at some constant rate V, I've added a dKdt equals minus V, that works. So we can decrease K gradually enough, again, not necessarily in discrete stair steps like change K, let the system respond, change K, let the system respond, but that's how I've drawn it. Change it slowly enough and control works. So this is how those two equilibria are moving through time as we're decreasing K, and the system tracks it, not perfectly. It never quite gets all the way to this N1 star because it's chasing a moving target. But what it actually collapses onto is the equilibrium point of, in this paper where I found this model they call the moving frame variable, which looks at the distance, the difference between the change rate in the population and the change rate of this knob returning. Essentially, is the system and chasing the environment. Okay. And the equilibrium of this is where that time series line actually collapses onto. So there's some very beautiful math here that's theirs and not mine. And it's why I'm using this model, even though it's not a great model of an invader. But this is the punchline. If we decrease K too quickly, here that's infinitely quickly, so there's no response until we're done changing K, then we get R tipping. So whoop, we cross that line, the hump we didn't want to cross. But no matter what, the stability lanes, the potential for N here, for our invader always looks like this. We never lose this, right? We're just moving it as we change K, but we never lose this, right? So it's not B tipping. It is R tipping. And fascinatingly, if we look at the potential for this moving frame variable Y, we do see a bifurcation as we increase the rate that we're changing K. So this is the no R tipping case. This is the, right on the threshold. And then this is the case where we do R tip, we're changing K too quickly. We no longer have an equilibrium in this moving frame variable. And so I think if we want to figure out, now 5 minutes over, so I'm going to shut up momentarily. But I just can't, because this is kind of a plea for help. I can't help it. If we want to figure out how to find the critical rates corresponded with rate-dependent tipping, I think it all comes down to figuring out the correct moving frame variable and doing a bifurcation analysis on that. And I don't know how to define the moving frame variable except for the one models that I find in these papers where they already have one that works. So that is an active area of research, and if anybody can help me, that's awesome. So to conclude, tipping points occur when something disrupts the slow dynamics that had previously preserved the regime. That can be a flat spot where noise is moving you off the flat spot. It can be a bifurcation that eliminates a flat spot, or it could be a change in where this flat spot is that's faster than the ability of the ball to roll to stay on it. And I think it's important just to remember that rate-dependent tipping happens because ecological systems can't respond instantaneously to changes. So the very thing that make us have interesting long transients and interesting dynamics in ecology are also the things creating this rate dependence. And I think there's a lot of opportunity to learn if we connect those fields a little bit more. So sorry for going over. I was really excited by the end part. So thank you for thumbs upping me and letting me keep going.
Yep. Thanks, Karen. That was really, really cool. Any questions? Yep. Yeah, you need a microphone. There's one there. Thanks.
Thank you very much for amazing talk. I have like two pedantic questions. First one, like about quasi-potential, I'm not sure that you really need to say quasi-potential because even like with the ball and gravitational potentials, there will be oscillations. So like it's, maybe you can still call them just potential, because like even like in gravitational potential, you will have like this like strange nonlinear dynamics. And second question is like more serious. And I very like the example with coyote, so I will use this also as example. when coyote run, he sometimes like run, and for some time he like running on the air, and for some time he is still not aware that he actually crossed the tipping point. So my question is that, like you said, the regime change happens when tipping point is crossed, but actually it's more like after the tipping point is crossed, and it's like
Yes.
Yeah.
Actually, that's beautiful. That's a great question. So I also like that you asked two questions and you said more serious, but then it had the coyote. So it's beautiful, beautiful. Yeah. So here's the thing. When the coyote runs off the cliff, no, it's not when the coyote runs off the cliff. When the coyote runs off the cliff, yeah, you're right. He just doesn't look down. So here's the thing. You imagine he's like on the cliff and it sometimes breaks off under him and he hasn't noticed yet. And that was the bifurcation. And now he's on the ghost attractor. And it's not till he looks down that, somehow, I think when we were talking about ghost attractors with my collaborator group that I've named here, we talked about that, like, just don't look down phenomenon quite a bit. And I think that the analogy actually works to cover, the coyote taught us everything. We really should just be out there watching cartoons. Thank you, yeah, Dave.
So from, I guess, an empiricist point of view, there's a lot of challenge in sort of detecting, early warning signs of regime shifts. Do you think, just based on some of these simulations you've done, that there's any sort of information contained in different types of early warning signals that could then inform us about what sort of tipping points, be it B, R, or N, that is going on?
Yeah, so all of the early warning signals that I am familiar with, which is not all of them, but so to the best of my knowledge, which is not probably all the way complete, those are geared towards anticipating B-tipping only. So I don't think we yet have things to look for, like the signature of an impending R-tipping event. Certainly noise tipping is, that's just like, boop, you got knocked over by a storm or something. So that one's a lot harder. But even in the B-tipping early warning signals, there's like increasing variance, for example, as one of the commonly used early warning signals. In a multi-species system, you're not going to see every single species increase in variance to the same degree. You're approaching the bifurcation, you're losing stability in some very specific way, right? So a theorist would say, in the combination of species, the linear combination of species abundances that fall along the dominant eigenvector, right? What does that mean in nature? Like nothing you could possibly look for. But it tells us why, like, in any given multi-species system, there's going to be a species or a subset of species that are going to most strongly show that increase in variance. And there are probably going to be a large number that, even if you had perfect detection, would not show an increase in variance. And so I think the use of early warning signals in general to anticipate even B-tipping is a lot more problematic than we really know how to deal with. It doesn't mean we should give up. I think it's a thing worth working on, but there's a lot more work to be done there. And then that's still just B-tipping. So I think the depressing answer to your question is like, no, not really.
All right, sounds good.
One very quick question, if anyone has a quick one. Owen, yeah.
Yeah, thanks very much, Karen. Really nice explanations and interesting research. I'm not really up to date with this literature, so just wondering what evidence. I mean, I know some of the evidence for the B-tipping.
Yeah.
Right, but what evidence is there for what examples of systems with R? Yeah,
we just had a paper, I think it's out online in biological conservation, and we really tried to find empirical examples of R-tipping, and to our knowledge, there aren't any. So now this is a statement of faith more than of science. I think that it happens a lot, but we didn't know to look for it. Also, it's really hard to say, if things had warmed but a little more slowly, that wouldn't have changed. Like I think it can be done experimentally. I think there might be some work on pollination networks led by a postdoc of Yingcheng Lai's that is going after that in an experimental sense. But yeah, what evidence is there? None. I really believe it's relevant to the real world, but I absolutely couldn't show you a data set that backs up that point. So yeah, it's a good question.
Excellent.
All right,
Well,
thank you, everyone.
thank you very much, Karen.